Hi, everybody. I'm Mike Heumann from G2M Research. Thank you for joining the G2M Research and Kioxia webinar today on why flash memory at scale should be software defined. Let's go ahead and get started. We are recording this webinar, and we'll make that recording available to everybody who registered for the webinar. So let me introduce things and give you a few ground rules, just things to make things easier. So here you can kind of see what our schedule is. We've got a presentation. We're going to break it in half with a live survey. We'll also have a short demo. You can put in questions anytime you'd like. Just use the Zoom question and answer window. Please put them in there. Don't put them in the chat. And what we'll do is as we go through the presentation, if you have questions, just put them in. And we'll hit all those questions at the end. This should take a little under an hour. My expectation is probably about 50 to 55 minutes. Again, this is being recorded, and we'll provide a copy of the recording to everybody who actually signs up, who is a registrant. We'll also send everybody who's a registrant a copy of the PDF of the slide set. All right, let's go. So what is flash memory at scale? It's an interesting term. So for us, what it means is using flash SSDs in extremely large data centers. In this context, you can think of people like Amazon Web Services, Microsoft Azure, Google Cloud, the BATs in China. Also, companies that provide software as a service capabilities. That includes Salesforce, Facebook, CDNs like Akamai, Twitter, Netflix. All those sorts of companies are really cloud service providers. So that's what we're looking at from. The unique thing for these companies is standard storage solutions oftentimes do not meet their needs. There's latency and throughput issues to think about. Most of these companies have service level agreements that they have to meet with their customers, and they have special approaches for aware management and redundancy. So just taking a standard off-the-shelf SSD and plugging into their data center generally doesn't work for them, or it's not optimal. They also might want to introduce their own technologies in the flash storage solution they provide. That could be their own firmware, it could be encryption, it could be any number of things. So that's some of the things that we're going to talk about in this webinar. So let me introduce Earl Philhauer. Earl's a senior staff product manager at Kioxia. Again, my name is Mike Heumann. I'm the principal analyst at G2M. And with that, let me give Earl back control of his screen. And Earl, it's all yours.
Thanks, Mike. And thank you, everyone who's attending, and spending a little bit of your day with me this morning or afternoon, as the case may be. So the title of the talk today is really why flash memory at scale needs to be software defined, why it should be software defined. And if there's one thing I've learned after working with major cloud providers and storage developers, is that they're absolutely in love with flash memory and how it's changed the data center. But what's not to like? I mean, it's got no moving parts. You have gigabytes a second of bandwidth in a single drive, terabytes of capacity in a 2.5-inch or smaller form factor, and access latency measured in microseconds. But now that the flash has been deployed throughout the data center, the storage developers are looking for a way of improving the efficiency, doing more with and better things with what they've got already in there. And this has led to several new requirements for flash that I've run into. Latency control for IO operations, because not all IO is the same. Not all IO is the same importance. Not all IO can take the same sort of delays. Some can handle it, some can't. You need to be able to prioritize in flash. I've found that migrating between flash technologies, because, hey, Kioxia, we make SSDs, we do flash memory, we're the inventor of it. We make a lot of generations, and you want to be able to migrate between these generations and these technologies of flash easily. So are you going to have to rewrite your application to take advantage of the next SSD in the pipeline? The bandwidth and the compute balance is also an issue basically because there's so much available bandwidth. There's so much you can do with this flash. You can saturate your CPU, you can saturate your DRAM, you can run into other bottlenecks if you're not careful. So you really want to be able to balance the compute and the bandwidth side. And finally, for cloud scale providers, especially when you're talking about a shared infrastructure, you have many, many different tenants running on a single server on a single drive. And you need to be able to isolate those workloads. You can't have one tenant that can disrupt the IO performance of another. That's really a way to make all of your users unhappy. So let's take a little deeper look at these 4 different needs. Now, latency control, that's a pretty major concern when you talk about flash at scale. It's really more about latency distribution than control, to be honest. Number 1 here, we have a nice low average latency with a few outliers. Or we have let's say have a different SSD with maybe a little longer latency, but a much tighter constraint on that latency. Which one's better? Well, neither really. It depends. Flash that's tuned for one extreme is not going to do well on the other. So for number 1, for example, where the latency is average, very low, but there's occasional outliers, that might make sense for something like, say, a time critical ad serving thing where, a microsecond is the difference between winning and losing. But the second one, where the average latency is much more constrained, but longer, it makes a better fit for, say, example, an RDBMS or a scale out database of some sort where all nodes need to report in, and those outliers in the other case would become an issue. It all depends on the requirements, and those requirements are going to change over time. And a single hardware defined flash configuration really can't solve both of these points here. You really need to have some sort of software definition. Migration, now moving between different flash technologies, different flash vendors, different flash generations. Now, each generation of flash has its own performance and latency profile. Bits per cell, people are talking about moving from TLC to QLC for some workloads. They work best at different IO profiles, and different vendors obviously tune their drives for different workloads. So you're faced with a choice as a storage developer. Are you going to optimize for that one drive that you've got installed today, very low level, and squeeze a maximum performance that you can out of it, to squeeze the maximum transactions a second or whatever? Or are you going to work at a higher level? If you go at that low level, you've got the issue of massive rewrites if you move between technologies. If you go at that higher level, you potentially are leaving some performance on the table with the benefit of being able to port quicker. So which one's better? Again, it depends. Right? It's some way of defining the performance characteristics, the latency characteristics of an SSD in software for the storage developer can avoid the downsides of either of these choices. Now, bandwidth compute balance is actually something that's really come up significantly with the advent of NVMe and at large scales. Even the PCI Express bus and DRAM buses in a modern server, they can be swapped by having multiple drives in the system. So, for example, you've got many at-scale databases, right? They do perform a periodic read and compress operations to get rid of dirty pages, get rid of old data. In typical drives, you really need to read and process in the CPU core and write back that data. Now, this can saturate the PCI Express bus with really only 4 or 5 NVMe SSDs in a server. And today, I can very easily buy a server with 24 NVMe slots. So is a bottleneck going to be the PCIe bus? Is it going to be the system DRAM bus, or are you going to run out of DRAM itself for doing these housekeeping operations that really aren't adding value on the CPU side, but are necessary for the data storage? Or are you going to run out of CPU cycles to actually do this copying? It depends where you want to do this. So being able to have some software control over how these work, and software way of saying keep the data in the drive until I actually need to do something useful with it, that can be a game changer. And finally, at cloud scales, at large scales, every system is a shared system. There's very, very few servers today that are running a single workload at scale. And when you've got multiple people all working on the same server on the same drive, you're going to run into the issue of noisy neighbors, just like when you were in college in the dorms and your neighbors on either side were, playing bongos while you were trying to study. It affects your performance negatively, and it affects IO performance negatively when heavy IO workloads in one, say, container or VM interfere with the processing of another higher priority VM. Now, managing the different priorities between these VMs, isolating the IO performance between different containers or VMs, that's something that really needs a software driven responsive way of prioritizing, of guaranteeing fairness. And it depends. You can't do one size does not fit all. Round robin, everybody gets the fair shot might make sense in some workloads that are batch. If you're having, say, interactive workloads, you want to have those obviously of higher priority and leave the streaming long latencies at a lower priority. A single drive with a hardware defined configuration really can't meet those needs very well. So at scale flash, you're looking for things like latency control, like we talked about. Really, the software developer, they want to be able to let the application prioritize the IO, because the software developer, the storage developer, they know that which IO stream is more important than others. They need to be able to migrate between different drives, drive technologies, vendors, flash generations quickly without giving up excess performance or control. You can only, take the benefits of all these wonderful new flash technologies that we're generating and putting in the marketplace today. You can only take advantage of it if your application can use it. And you need to be able to make sure that the storage developer can define their own requirements for these flash and not really be constrained by the hardware. You need to also be aware of the bottlenecks in servers today, especially with high-speed flash storage. The balance between bus bandwidths like PCI Express or the DRAM and the compute side, your CPU, that's very important. And the way to do that is really a software-defined way of saying, don't move data into host DRAM that you don't need to actually process with the CPU. And finally, you need to be able to preserve the responsiveness of your workloads you care about, without letting high IO workload VMs or containers break your SLAs. The only way I can see to do this, and most people I've spoken to, is to make flash software defined. And that's really the key to the talk here. How can we software define flash? How can we make it more accessible, more valuable, more usable, let you get more out of it as a storage developer? And we'll look at that a little bit in more detail with one of Kioxia's solutions for doing that. But first, let me pass over to Mike, who has our survey question. Mike, would you like to take over?
Sure, you can actually just go to the next slide.
All right.
Control at this point. So we are going to launch a survey right now. It will show up in the Zoom survey tool. And the survey is, what is the biggest challenge with flash storage at scale? A, unpredictable or undesired latency outcomes. B, difficulty moving between different flash memory generations or products. C, bottlenecks in the system that limit the results or performance. And D, keeping application SLAs in the presence of other applications on a server, basically multi-tenant. So we'll give everybody a couple of minutes to go ahead and answer this. And we'll put these answers on the PDF of the slide set when we send it out on Thursday. And with that, Earl, let me turn it back to you.
All right. Should we, is this going to block their view, or should we give him a few minutes to before we advance?
No, you can go ahead and advance. It won't block the view.
Okay, well, so I know which one I'm thinking of, but I'll be very interested to see what the crowd response is, because they're all, depending upon where you work and what your need for storage is, I can see reasons for all of these. So let me continue then. Thanks, Mike. So software-defined flash, we have something called software-enabled flash technology, which here at Kioxia is our solution for software-defined flash at scale. Whether you're talking about using software-defined flash as say a cloud provider, as a internal systems provider, as a storage developer, as somebody developing, say, large storage systems for other companies. So the key here is software defined, right? The cloud today, every data center in the world, it's based on software defined. You got software defined networking components, all the way at the top of your rack. You've got software-defined accelerators. You even have software-defined CPUs. Intel has recently put in patches into the Linux kernel that can let them potentially change the performance, change the opcodes available in some of their upcoming Xeon processors. So you've got the software-defined layers, even down to the software-defined storage, where you're doing your scale-out storage of massive scale between multiple nodes. But you've got the software from top to bottom, but not all the way at the bottom there, right? That lowest layer of the stack where the data is sitting, the flash itself, it really hasn't been software-defined in any meaningful way. And software-enabled flash gives you a way of doing that, of changing that whole idea. So software-enabled flash, it's a media-based. For that really means it's flash-based, host-managed hardware approach. And we'll talk a little bit about that in a few more slides. But the message or the important point is that it redefines, it changes the way the storage application, the server, the host interacts with flash, and it allows the applications to maximize performance and give functionality that would be difficult or maybe even impossible with existing interfaces. So it's a new interface. It's a new hardware design that gives that host control. The host can now finally define behavior and performance characteristics of the flash instead of just taking what is hard coded in the drive. They're able to configure it on a per workload basis, changing over time as workloads change. Now, this can enable new storage functionality that maximizes the performance and efficiencies. Or the way we like to say it, software-enabled flash gives you the ability to extract the maximum value of all that flash that's in your data center. Now, this is a high-level block diagram of the controller itself. It's a little technical, but the interesting thing here is that this is a new hardware design, and the controller itself is contains all of the information required to control the flash proper. So things like how do you program the flash properly? How do you make sure the flash wears at an even rate? How do you handle defects as they come up? That's relatively common. You find that in most drives. But what's interesting here is the fact that the hardware itself has multiple queues that are prioritized by the application for different IOs that go per flash die. It also has a very powerful copy offload functionality, which can preserve PCIe bandwidth, and I'll talk about that in a little bit, while saving CPU cycles as well. And it's a unique design. It's not something that runs on existing drives. It's on software-enabled flash drives. Now, this software-enabled flash obviously needs software above this hardware to do anything, just like everything in the world. So Kioxia has built an entire stack, starting with a software-enabled flash device driver, which is based on the existing NVM Express device driver. So this is working under Linux. Then the key here is above that, there's a simple API that lets software, that's storage developers, directly tell the drive, I need this sort of latency profile. I believe that this IO is more important than the other IO, that I need to perform background operations right now or not now because I'm in the middle of, say, Christmas rush and, my orders are coming in too fast. This API above that, we also have a software development kit that's coming out very soon that implements something like implements a way of using this software-defined flash without writing a single line of code for, say, virtual machines and containers. Now, what's interesting is if you look on the left-hand side, you see it's kind of an L. The API is available to the applications, or the applications can actually go through this block device driver. So it's a staged software development effort. It's not a complete say forklift upgrade. You're able to get some of the benefits just using the SDK. And then as you progress and you want to get more control, where you need to get more advanced scheduling options, you can actually go through the API directly to the hardware. So what does this mean, right? I've thrown out some kind of techie slides where I looked at hardware configs and software stacks. To the storage developer, those are cool, but what does it mean? How does it maximize the flash value at scale, as we like to say? Well, again, the same four problems that we've got: the latency control or latency outcome control, ease of migration, computation, bandwidth, balancing, and isolating antennas. How does software-enabled flash work with each of these? How does it help address these problems at scale? So let's talk about latency control. Now, software-enabled flash provides a unique queuing operation. As I talked about earlier, the hardware itself has these flash queues, and it's a unique in the industry, where you can set priorities between different IOs and assign them to different queues, and that gives you amazing power. We provide 3 different ways of controlling the queuing and the IO priorities between applications. We can do simple IO, static priorities, 1 through 8, the highest one wins. We can do round robin, so everybody gets a fair shot. Or what is very interesting is we're able to provide a die time weighted fair queuing mode, where IO operations are able to be prioritized on a per IO basis, a single read or write, between all of the other competing requirements of the system. So this really helps configure whether your latency, 1 or 2, whether you're low latency with a few outliers, or maybe a little longer latency with a tight latency spread. This lets a software application choose on a per application basis, changing over time, which makes the most sense. And I've got a neat little demonstration here, which is using this weighted fair queue to perform a real-time change of the SSD characteristics. And it's something I don't think I've ever seen in any other drive or in any other way of using flash. So let me pop that up. So this is pre-recorded, on a real hardware. This is not a simulation. And what we've got here is we're going to have two different workloads, workload 1 and workload 2. One will be red, one will be blue, and we'll see the latency. Obviously, low latency, you want lower is good, upper is maybe not so good, or longer latency. And we have the priorities between them, the weighting, as we were talking about in the prior slide. And we'll see how, as we adjust the weighting in real time with this bar, we'll actually see the latencies of the different workloads adjust accordingly. So let me just start it up and we can see. Initially, they're even, but let's say it comes in and all of a sudden I want to make, let's see, workload, I believe 1 is going to become more important. Let me pop that in. Actually, workload 2 becomes more important, so it has a lower weight. We see the latency of the IOs, the same test. It's not been stopped. The test is still running the same test. Just changed. The blue guy was reduced latency at the expense of the red guy, and vice versa. Software-defined control over the latency outcomes of a running system without application intervention, right? These are two completely different workloads running, a simple FIO, a simple block-based IO tester. And we're able to adjust and get different latency outcomes in real time. We're doing it as a human, but this is something that an application or an orchestration layer would be handling in the clouds. And that's a very powerful feature. It's a very unique feature of software-enabled flash, the ability to adjust in real time how your workloads behave. So let's pop on to the next one. So that was the latency control. Now, the next issue was really migration. We talked before about how developers, you're kind of, as a storage developer, you're kind of stuck between choosing between optimizing for, say, a single flash drive type at the cost of portability to other flash and the cost of development speed, or abstracting your IO stack and working at a higher level and maybe leaving some performance, maybe leaving some flash value on the table. Software-enabled flash, thanks to its software-defined abstraction, it can help avoid this trade-off, help avoid having to make this trade-off in the first place. With software-enabled flash, the application's IO stack is explicitly requesting things like the latency, prioritization like we just saw, or the workload isolation, as we talked about earlier. And the software-enabled flash API and the special purpose hardware actually handle the low-level implementation. The storage developer says what he needs as opposed to has to figure it out for every individual drive. The app doesn't need to be concerned with the underlying flash technology, and optimized IO stacks can be optimized and minimize the differences, minimize the porting when new flash is brought in. Things just work is the key here. This gives you a much faster speed of development, a much shorter development cycle. It minimizes the amount of capabilities of flash that you're leaving on the table. And hopefully, this lets you get newer flash into your data center, into your demanding workloads faster and get more value out of the entire system. Now, balance. How do we handle having many NVMe drives in a single server? How do we make sure that we don't saturate the PCIe bus doing silly things like collecting garbage collection or compacting a database where there's really not a lot for the CPU to do other than read and write. Well, software-enabled flash has offload operation. We call it nameless copy. On the left-hand side is manual copy, which is a standard way where you perform reads and writes at the app level, saying, read this block, read that block, read the other block. You'd store it in your application DRAM, and then you'd write new. On the right-hand side, we abstract it. We move it to a higher level. We let the software-enabled flash controller with that special purpose hardware, you tell it what to do and it does it. You give it a list in effect. So let me start. We've got a cute animation here. Now, on the left-hand side, you'll see things are going through DRAM and they're going through the PCIe bus to get to that DRAM. And then eventually it goes back out from the DRAM into the PCIe bus. That's traditionally way. It's a significant amount of work on the CPU, just handling the silly IOs. And a lot of DRAM is wasted buffering these, and a lot of CPU cycles and application performance is kind of left on the table. Using the offload operation, which we call nameless copy in software-enabled flash, we can actually tell the drive, the storage developer tells the drive, collect these parts of the database file and move them to a new block. Collect these parts of the flash translation layer and move them around accordingly. No data has to be transferred from the drive to the host. The CPU in the host is free to actually do useful stuff like serve your users. And the DRAM is not required. You're not actually wasting host DRAM storing these temporary buffers. It's a very neat tool. It's a very powerful tool for optimizing at scale when you have multiple drives in a system and you've got multiple heavy compute workloads. And again, that's software-enabled flash with the special purpose hardware to do that. Now, finally, isolating tenants. How do we keep one workload from hurting another workload and software-enabled flash? Well, we've got a couple ways of handling that. We've got a hardware-based isolation, which is almost equivalent to, say, physically partitioning up the drive into specific units that only specific workloads are able to touch. What's neat about that is that because of the way flash works and the controller works, when you partition that way, individual workloads in different, we call them virtual devices here, and these different hardware isolation groups can't interfere with the others because they're working on different flash die. They're actually writing to different spots on the card, different chips. So that's a super powerful way of saying I have very absolute IO needs that I need to keep separated. Now on top, and this is great, and lots of workloads, this is 90% of the way there to getting what you need. But we also have something called quality of service domains. It's a fancy way of saying a software-based dynamic isolation. Now, this is where the queuing comes in that we talked about earlier. These are dynamically configurable, and they work on top of these hardware isolated units to give you a kind of a second layer of control over IO prioritization, over latency outcome control, over making sure that one workload doesn't stomp on another workload. We're able to both slice up the capacity, the latency profiles, the bandwidth profiles accordingly. And that's, again, through the software-enabled flash API and SDK. So the software layers, the storage developer simply decides that I have a need to configure the the IOs in this at this time, right? Because it's dynamic, I can change it as I'm running. At this time, app A needs to get higher priorities, or app B is coming up. It's a nightly run, it's a batch run, it can be low priority. I can push that down. Now, this lets the storage developer really explicitly manage the finite IO resources, right? I mean, there are limited resources on these drives. It lets the storage developer pick and choose and say, this is what's important, this is not. And it's all application defined. And it's really, really cool. So in a nutshell, software defined flash at scale, I'm going to say that's really software enabled flash at scale. It's clear that you can do more with flash, that you can get better results with flash. You can get the most value for the flash you've got installed or will install in your data center if you make flash software defined like the rest of that data center. And software enabled flash is really the way of doing that. It gives you the fine grained control, controlled by the application, controlled dynamically to configure latency outcomes. You can tune for low latency. You can tune for low variability. You can tune for one workload at the expense of another. Dynamically, again, it's all under application control. The storage developer has the power, not it's not what's hard coded into the drive or the operating system. Software enabled flash, it allows for faster and easier migration between flash technologies, flash generations, even flash vendors. You're not forced to choose between optimizing and getting the best capabilities and best performance for your flash for a single type of drive, or for abstracting and allowing quick portability. Because you're able as a storage developer to explicitly request specific latency, IO latency, and tenant isolation profiles and priorities, the application IO stack just works with the flash and the software enabled flash special purpose hardware handling the lower level details to make sure that your requirements are met by the system. Now, the bottlenecks too, we saw that really cool demo where we're able to compact the database effectively without actually having to move any data into the host CPU, without using any CPU cycles. This software-enabled flash offload can help avoid PCIe, DRAM, and CPU bottlenecks. Data can be kept in the drive, moved in the drive until there's actually something valuable for the host, for your storage application to do. Instead of your storage application being a simple read writer, you're able to actually tell the drive to do the grunt work, and your app frees the CPU cycles for serving your customers. And finally, the software-enabled flash gives you two different ways of isolating workloads and the performance impacts of those workloads from one another. And this is absolutely important if you are working in a shared environment, which everybody is today. Every cloud today is running more than one workload on a server. This lets you deploy multiple workloads on a single server without having SLAs randomly broken by, say, noisy neighbors, by high IO throughput, high IO requirement applications. The hardware and software partitioning of software-enabled flash really gives a powerful way of keeping the one tenant away from the other. And in a nutshell, summing it up, I mean, software-enabled flash, it's the most powerful way I know of making flash software defined and getting the most value as a storage developer out of flash today. So software-enabled flash, we said this before, it changes the way, it redefines the relationship between the host, the application, and flash. It's got software, it's got a special purpose hardware, uniquely tuned with unique features out there to prioritize application requirements. and it's got a open source API and SDK built on top of that to let the software developers, the storage developers, actually go and get the most out of it. It's based on industry standard protocols like NVMe, as I was talking about, and it gives full application control, full host control of the flash relatively easily. I mean, it's a unique set of features, and it's a way of getting software defined into the flash drive itself and all the way into your storage stack. So we do have a website at softwareenabledflash.com with quite a few white papers, videos, infographics. It can give you a more in-depth view of what software-enabled flash is, how it affects different workloads, and some other demos that we've got too. So those are pretty neat. Now, I think we've got a few minutes. Mike, have you been looking at the Q&A section?
Yes, I have. We've got a couple questions here, some of which you just answered in the last slide, but that's okay. I'll ask the questions anyway. So one of the first questions was, are these capabilities available on all Kioxia SSDs, or are there specific ones that it's available on?
Oh, that's a very good question. So are these available on all Kioxia SSDs? The answer is no. These are software-enabled flash units, we call them drives. They are a new technology. They're not general purpose. They're not going to be replacing, say, client drives. They're really for some flash at scale. So it has to be a software-enabled flash that has a special purpose hardware to interface with the open source API we talked about in the SDK.
Excellent. One of the other questions was, what sort of security measures are there on who can actually use these APIs to program the flash?
Hey, that's actually a really good question. So security measures. Now, obviously in a shared system, security is paramount. You don't want one workload to be able to spy on another, especially when you don't control those workloads. Now, I didn't go into it in here, but software-enabled flash, each of these, let me see if I can pop back to the slide for a little bit of descriptions here. So each one of these domains, each one of these software isolated units, number one is able to have its own encryption key that's handled by the application. So the data on the flash can be encrypted on a per app, per workload basis with the hardware. And above that, because it's Linux based, it hooks into the standard Linux permissions model. So things like the different authorities that are granted to different users or different workloads, which would obviously be running under different user IDs, is also respected. So it's you need to have administrator access to actually make these domains, and then you can actually lock down the domains. Same as if you were trying to lock down, say, a file system. So that's a good question. I didn't go into it because it's a little more, it's a nuanced thing. But
no, that's a great answer. And I guess it makes it really, so if you're really doing real multi-tenant, any given application can do its own tuning if it needs to, which is really cool.
Yeah, that's the key. It can do its tuning, and you're able to adjust dynamically, right? I mean, that's a real key with the software defined, is as the needs change, as the workloads change, the storage developer can say, hey, this is important, this isn't important. Hey, I need lower latency on this one. Hey, don't garbage collect, don't do any background operations during this period. Those are the kind of what got us interested in software-enabled flash in the beginning, when we heard those requests from the large scale storage developers.
Excellent. And the last question that there was, how are these capabilities complementary to some of the things that have been added to the NVMe spec over the last year or so?
Okay, so how are they complementary to the NVMe spec? They're complementary. I mean, I'm not quite sure I have a good understanding of what's being asked, but let me do my best. This is based on NVM Express. It provides a whole new set of capabilities, a lot more advanced than what's out there in the NVMe, I guess 2.0 out right now. The way it works is kind of at a finer grain of control, a finer level of detail, a finer level of control. The fact that it is based on both hardware and software is really the kind of the, let's see if I can pop back. I have a picture. It's based on both custom hardware and a software stack is really unique, right? NVMe is a simple, it's a simple hardware API. It's not that simple, but at the end of the day, it is. The software-enabled flash is more about having application level requirements. I need this kind of latency. I need that kind of isolation, as opposed to the lowest level NVMe spec. So I hope that kind of gave a view. We have somewhat more information at a more technical level. If you want to look at the softwareenabledflash.com, let me pop their website up. I'm sorry. Yeah, so at the softwareenabledflash.com website, you can get a little more detail on how they work together and how they can do more, or how software-enabled flash can do more than a simple hardware level specification can.
Outstanding. No, it sounds like it's really an extension of the capabilities that NVMe has, like you said, a much finer level. So
that and the software layer on top is really the key, right? I mean, you can provide the IO, the low level control. There are some of them. Some of these features are very basically implemented in the new NVMe 2.0 spec, but the level of software control, the level of, hey, this is what the user needs, as opposed to say what the hardware developer needs, I think is very different here. And I think it's a lot more interesting when you're talking about it, flash at scale.
Absolutely. Well, thank you, Earl. And thank you, everybody, for joining. As I said at the beginning, we'll be sending out a recording of this webinar along with the PDF of the slide set sometime on Thursday. We'll send that to everybody who registered. Again, thanks, Earl, for a great presentation. I think this is really good information. And our next webinar with Kioxia on software-enabled flash will be on November 17th. That will be again at 10 a.m. Pacific. We hope that you guys can join us there. Some information will be going out on how to sign up on that shortly. And with that, thank you, everybody. And I hope everybody has a great day. Thank you, Earl.
Thank you, Mike. Thank you, everyone, for giving me a little bit of your day. I hope you've learned a little bit. I've had fun. I hope you did too.
Have a good one.